Hello, and welcome to Zetec's webinar on our UT inspection solution for HDPE butt fusion joints. My name is Michael Mussman of Zetec. I'd like to thank everyone for joining us today. As an on-demand webinar, there is no live question and answer section at the end. Instead, you can email your questions at any time to webinars@zetec.com, and we will respond directly back to you. Before we begin the webinar, I'd like to give you a quick overview of Zetec. Zetec is a global NDT leader. For over 50 years, we've advanced the science and standards in both ultrasonic and eddy current technologies, setting new heights in inspection performance, productivity, and predictability. Zetec's proven expertise and complete product portfolio serve the inspection needs of our customers worldwide in transportation, power generation, manufacturing, and oil and gas. Zetec is a subsidiary of Roper Technologies. Let's get to today's session, which will be presented by Guy Maas. Guy has been involved in advanced UT method development and implementation, capability assessment, and software development for more than 25 years. Since 2000, Guy has held various positions at Zetec and RD Tech, including Sales Director, Product Manager, and UT Applications Manager. Guy is currently the Sales Engineer Director UT at Zetec. With that, I'd like to now turn this webinar over to Guy.
Thank you, Michael. Hello, I'm Guy Maas, and I have the pleasure of presenting this webinar about our UT inspection solution for HDPE butt fusion joints. And this is our agenda for today. First of all, I will give an introduction on high-density polyethylene, or HDPE, the benefits of using this material for piping, and the characteristics of the butt fusion process used to join the pipes together. I will discuss the challenges related to UT examination of HDPE butt welds, and I will introduce the key elements of the recommended UT inspection solution. After that, I will use two representative HDPE butt joint specimens to illustrate how the UltraVision software is used to optimize the different inspection techniques for a given configuration. I will also talk about Zetec's TOPAZ family of high-performance phase array units and how the various models support all the previously discussed inspection techniques. We will then take a detailed look at the examination results obtained on the specimens containing representative reflectors. A TOPAZ 64 phase array unit was used for data recording and the UltraVision Classic software for data analysis. The benefits and limitations of each inspection technique will be addressed. And finally, we will wrap up with some conclusions from the presented material. High-density polyethylene, or HDPE, is a plastic resin made from petroleum. It is a thermoplastic, which means that it can be remelted to shape, reform, or recycle the material. HDPE pipes are being used instead of carbon steel pipes for low pressure and low temperature conditions in the petrochemical, power generation, and mining industries. And more recently, HDPE has also been used for nuclear, safety-related cooling water applications. The use of HDPE has various advantages. For example, it has exceptional resistance to corrosion and erosion. It is a tough, durable, and recyclable material. It is lightweight and therefore easy to transport. And it has flexibility for quick installation. And quite important, it requires no flame for joining, and there are many fitting and joining options. HDPE pipes can be butt fused by applying heat and pressure to make a permanent joint. The two ends of the pipes to be joined are dressed flat and square to each other, and then heated using a flat heater plate until a molten state is attained on each contact surface. The two surfaces are then brought together under controlled pressure for a specific cooling time, and a homogeneous fusion joint is formed. The performance under pressure of this joint is comparable to the pipe itself. The HDPE butt fusion process is typically subject to the following flaw types: lack of fusion, cold fusion or partial bond, embedded inclusions, and voids. And obviously, non-destructive examination is often requested to detect these flaws. HDPE material has specific characteristics that make ultrasonic inspection challenging. First of all, its acoustic impedance and sound velocity are similar to the materials commonly used for ultrasound wedges, which makes it more difficult to generate acoustic sound beams with the appropriate refracted angles. The material is also highly attenuating. Therefore, lower inspection frequencies are required compared to carbon steel inspections. And L waves will be used because the shear waves are too much attenuated. The vertical fusion phase of the butt joint makes the lack of fusion and cold fusion type flaws difficult to detect with phased array pulse echo techniques. And finally, the reduced overall signal-to-noise ratio may jeopardize efficient use of tip diffraction signals for through-wall sizing. Considering the challenges for UT inspection of HDPE butt joints, it is important to use a robust inspection strategy, combining multiple ultrasonic examination techniques, including pulse echo and tandem phase array, as well as TOFD. The use of carefully selected UT and phase array probes is important in order to optimize the performance of the applied techniques. In the case of HDPE, the nominal frequency of the probes will typically be 2.25 MHz or even 1.5 MHz for very thick components. The probes will be combined with high-angle Rexelite wedges to generate the appropriate L-wave beams in the material. The use of Rexelite wedges instead of water wedges facilitates the deployment of this solution in the field. Zetec's TOPAZ family of high-performance phase array units have all the tools and features to efficiently implement and deploy the techniques I just mentioned. The UltraVision Classic software is used to set up the Tandem configurations and, of course, for detailed data analysis. We will use 2 case studies to illustrate the optimization of the inspection techniques and the design of the scan plan. Our first specimen is an HDPE butt weld with an OD of 315 millimeters, about 12 inches, and a nominal pipe thickness of 35 millimeters, which is a little less than 1.5 inches. The specimen contains 3 millimeter diameter flat bottom holes located in the fusion phase at various depths. As you can see on the picture at the right, the specimen was machined to allow for introducing these flat bottom holes. These reflectors will be used to assess the detection capability on small lack of fusion type defects. The specimen also contains notches with different depth extent, introduced from both OD and ID surface. The notches are from 3 to 13 millimeters deep, which corresponds to 10 and 40% of the wall thickness. They will be used to assess the coverage and the sizing capability of the proposed inspection techniques. It is important to mention that the notches were hand machined and therefore their sidewalls have a certain roughness. Pulse echo phase array will be evaluated as a primary detection technique for ID and OD connected planar flaws and embedded volumetric flaws. For the considered specimen, a 1D linear array at 2.25 MHz is proposed. Our standard LM probe using an aperture of at least 32 elements. The probe is fixed onto a Rexelite wedge, generating a nominal 60-degree L-wave beam in HDPE. As previously mentioned, the use of shear waves is not useful given the extreme attenuation of this wave type in the material. This animation, with both ray tracing and acoustic beam simulation, shows the coverage of an azimuthal sweep from 48 to 78 degrees L-waves with an aperture of 32 elements. The beams are all focused on the fusion phase. The refracted angle range and the position of the active aperture in the probe are optimized to insonify the complete thickness of the joint with the first half skip. The efficiency of the detection after skip is strongly reduced by the mode conversion of the L waves, so this information is not reliable. The acoustic beam simulation allows us to assess the acoustic beam size for all angles in the sweep, roughly 5 millimeters in the incidence plane and 8 millimeters in the perpendicular plane. The phased array tandem technique is a technique that we can use to get improved detection capability on embedded planar flaws in the vertical fusion phase. To ensure inspection efficiency, a self-tandem technique can be implemented as a second channel from the same 1D linear array probe that is used for the pulse echo technique. My next video will illustrate how the UltraVision Classic software allows the operator to set up an optimized focal law set for the self-tandem configuration on the considered pipe specimen. The advanced calculator in UltraVision Classic includes a very flexible tool to generate focal law groups for self-tandem and dual probe tandem configurations. First, the operator selects the considered configuration and the wave mode from the probe tab. Then, the manual option in the focal law tab allows to select the required transmitter and receiver apertures and the position of the reflection plane, in our case, the fusion phase of the butt joint. A set of optimized focal laws can then be generated to maximize the depth coverage for the considered specimen. Obviously, the coverage will be limited by the obtainable angle range for the selected wave mode and by the probe position compared to the fusion phase. The animation shows that in this case, the LL-L self-tandem configuration allows to adequately cover the depth range from 10 to 30 millimeters, with roughly 20 near to specular focal laws. And this coverage complements the detection range of the pulse echo technique. For very thick pipes, transmitter and receiver apertures need to be further apart, so a dual probe tandem technique will be more effective to adequately cover the region of interest. And finally, we will also evaluate live TFM as an alternative technique for flaw characterization. The L-L wave mode will be generated from the same 1D linear array and wedge using the complete 64-element aperture. The final asset for our inspection strategy is the TOFD technique. TOFD is used for its effectiveness in detecting and sizing embedded and ID-connected vertical fusion flaws, as well as volumetric flaws. Conventional piezocomposite probes at 2.25 MHz will be used in combination with Rexolite wedges. On this specimen, we have used wedges generating nominal angles of 60 L wave and 45 L wave in HDPE, but a 70 L wave wedge could also be useful for very thin pipes. Like for carbon steel weld inspection, the use of several TOFD pairs may improve coverage and sensitivity on thicker components. This type of setup is also recommended by the ASTM E3044 standard practice for ultrasonic testing of HDPE butt fusion joints. Now that we have determined the key parameters for the individual examination techniques, let us summarize the different probe assemblies that we will deploy and look at the scan plan for this specimen. The two-phase array techniques, pulse echo and self-tandem, will be applied from both sides of the joint if possible, using two linear array probes with 64 elements mounted on the appropriate wedges. In addition, we have two conventional TOFD pairs for complementary detection capability and sizing accuracy. The TOFD technique is only applicable when we have access to both sides of the joint. The 6 probes can be mounted simultaneously on various commercially available scanning mechanisms, either fully automated or manually driven. A single line scan sequence allows to cover the complete examination volume adjacent to the joint according to the applicable codes and standards. In specific, this scan plan is fully compliant with ASTM E3044 as well as mandatory Appendix 10 of ASME Code Section 5, Article 4. Zetec's TOPAZ family of high-performance phase array units covers the requirements for a wide range of inspections. at different price ranges depending on the application. All units are running on the same user interface and therefore require minimal additional operator training when moving from one unit to another. With their onboard UltraVision Touch software, the TOPAZ units have all the tools and features to satisfy the requirements of the applicable codes and standards for HDPE inspections. For the case study that I just presented, both TOPAZ 32 and TOPAZ 64 allow to run all phase array and TOFD inspection techniques simultaneously at an industrial inspection speed of roughly 25 millimeters or 1 inch per second. The scanning time for this 12-inch weld with all techniques is less than 1 minute. With the standard splitter box, the two phase array probes can be connected to the TOPAZ unit. The two TOFD pairs are directly connected to the dedicated TOFD channels at 200 volts. The TOPAZ 64 offers a few features for additional performance. First of all, it allows to use an active aperture of more than 32 elements. Also, it offers the bipolar pulsar of 150 volts peak to peak, providing 40% more acoustic energy. These two features may become very useful to overcome the high attenuation of the HDPE material for thicker components. And finally, its high-resolution live TFM can be used as an alternative inspection technique for characterization of flaws. Let us now take a look at the examination data obtained with the different inspection techniques on this HDPE specimen. For the phase array data, we will typically have the following views on the screen: the VC top view, top left, the VC side view, bottom left, and at the right, the VC end view that shows the section of the butt fusion. On this first slide, we are looking at the merged data from the pulse echo phase array technique. We can observe that the 3 OD notches are very easily detected with a very high signal-to-noise ratio, actually more than 24 dB. This demonstrates that our probe assembly with the custom Rexolite wedge can efficiently generate high-angle beams in the HDPE material. Due to the geometry of the fusion joint and the use of L-waves, there is not a very good corner effect to detect the ID-connected flaws. Therefore, we must count on the weaker tip signals. This slide shows the same data with 6 dB extra soft gain. The strong attenuation of the material with increasing depth has been mitigated by the use of a TCG, and the 3 ID notches are well detected. The signal-to-noise ratio is still better than 16 dB. This slide also shows the capability of the tip diffraction technique to perform accurate depth sizing on ID notches and deep OD notches. Unfortunately, for shallow OD notches, the strong specular echo from the notch face hides the weaker tip signal. The last slide for the pulse echo technique shows the data from the small planar reflectors in the fusion phase, perpendicular to the surface. We can observe that 2 of the flat bottom holes in the upper half of the wall thickness are pretty well detected, with a signal-to-noise ratio comparable to the notches. We can see on the side view that the projection focusing mode provides very good resolution, and the tip diffraction technique works quite well for sizing of embedded reflectors. For the other 2 flat bottom holes, the signal-to-noise ratio is 6 dB or less, so we cannot claim reliable detection for those reflectors in the lower half of the wall thickness. Let us move on to the phase array self-tandem technique. Generate with the same probe assembly in the same scanning sequence. Again, we are looking at merged data showing images from the notches in the specimen. We can observe strong specular reflections and high signal-to-noise ratio from the deep surface-breaking planar flaws in the fusion phase. As we learned from the coverage assessment for the Tandem technique, smaller surface-breaking flaws near the OD provide weak signals and can be missed, as indicated by the red arrows. And here we see the data from the small embedded reflectors with the same technique. The soft gain was adjusted for the data analysis to improve the contrast. 3 reflectors in the mid-wall and ID range are clearly detected with a high signal-to-noise ratio. The reflector near the OD is missed, again, because of the lack of coverage in that region. So let me try to summarize the results of the two phase array techniques. I have used a color code to indicate detection capability. A signal-to-noise ratio of 10 dB or more is considered a reliable detection and is shown in green. Anything lower than 10 dB is considered not reliable and is shown in gray. We have observed that the pulse echo technique detects all the surface breaking notches and also the small embedded reflectors in the upper half of the wall thickness. And we have seen that the tip diffraction technique can be applied for accurate depth sizing. The Tandem technique provides very good detection of all reflectors except those located in the near surface range. And if we look at the combined detection capability shown in the rightmost column on this slide, the conclusion is that phase array UT provides excellent detection of all reflectors either surface breaking or embedded. This also means that we have a complete solution for HDPE butt joints that are only accessible from one side. My next slide shows the data from the live TFM in L-L wave mode. Like for the phase array pulse echo technique, we get good images from the OD notches, but the images from the ID notches have a lower signal-to-noise ratio than the standard phase array focused on the fusion line. And we can see similar behavior on the small embedded reflectors. We get excellent resolution on one of the reflectors in the upper half of the wall thickness, but near the ID, the signal-to-noise ratio is poor to none. Most probably, the attenuation of the HDPE material reduces the penetration of the single-element FMC firing mode. The TFM LL-L wave mode was also tested, but did not provide useful results for this configuration. After the phase array, let us look at the results for the TOFD techniques. This slide shows the data from the TOFD pair covering the OD region on top and the pair covering the ID region below. We can observe that between the two TOFD pairs, all notches are very well detected, some by both techniques. The next slide shows the data from the same techniques on the embedded flat bottom holes. Obviously, all four reflectors are very well detected and clearly illustrate the coverage and the accurate depth positioning capability of the TOFD technique. We must, however, be aware that the flat bottom holes also present a reflective surface for the TOFD techniques, and not only the edge in the fusion line. Therefore, this last image can be considered representative for the detection of inclusions and voids, but it overestimates the detection capability for small planar reflectors in the fusion line. This slide summarizes the TOFD results. In this case, the color code is not related to a quantitative signal-to-noise ratio, but it is based on a qualitative evaluation of the image. Still, we can observe that all notches and embedded reflectors are reliably detected. Using the low-frequency TOFD probes with appropriate Rexelite wedges, the complete wall thickness can be covered, and accurate through-wall sizing can be achieved. Even if TOFD can be considered as a standalone technique if the weld is accessible from two sides, it is a good idea to complement with at least pulse echo phase array to mitigate the weakness of the TOFD technique to detect very shallow OD surface breaking flaws. The second case study will be on a thinner component with an OD of 110 millimeters, a little over 4 inches, and the nominal pipe thickness of 10 millimeters, roughly 3/8 of an inch. Like the first one, this specimen also contains notches machined from OD and ID surface. The notches vary from 3 to 7 millimeters deep, and there are also 3 flat-bottomed holes located in the fusion phase. For the pulse echo technique on this specimen, a smaller 1D linear array at 2.25 MHz will be used, our standard AM probe with an aperture of 16 elements. The probe is fixed onto a Rexelite wedge, generating a nominal 60 L wave beam in HDPE. This slide shows the acoustic beam simulation for the selected azimuthal sweep from 60 to 80 degrees L-wave with a 16-element aperture. The beams are all focused on the fusion phase. The acoustic beam size in the cylindrical component is roughly 3.5 millimeter in the incidence plane and 5 millimeter in the perpendicular plane. And like in the previous case study, the phase array self-tandem technique is implemented as a second channel from the same 1D linear array probe. Using the Tandem focal law tool in the UltraVision Advanced Calculator, we get the set of laws shown on this slide. On this thin specimen, we can observe that based on the ray tracing, the LL-L self-tandem configuration allows to adequately cover the depth range from 2 to 10 millimeters with near to specular focal laws. This slide gives a summary of all the proposed techniques. We have added a TOFD pair using 2.25 MHz probes and a 60 L-wave wedge. Obviously, all wedges require appropriate contouring for the small diameter pipe. And this is what the scan plan looks like for our second specimen. We have the two phase array techniques applied with two probes from both sides of the weld and a single conventional TOFD pair. And like for the first specimen, this scan plan is fully compliant with ASTM E3044, as well as mandatory Appendix 10 of ASME Code Section 5, Article 4. For this configuration, all our TOPAZ units allow to run the inspection technique simultaneously and at high speed, in this case, a little over 30 millimeters per second. Scanning time for the small diameter weld is way below a minute. Even the compact TOPAZ 16 unit will do an excellent job. It allows to run all the focal laws from the two-phase array probes through its standard splitter box, and with the TOFD probes connected to the conventional UT channel at 200 volts. So let's take a look at the examination data from our second specimen. On this slide, we have the merged data group from the pulse echo phase array technique. We can observe that all OD and ID notches are very easily detected, with a signal-to-noise ratio ranging from 12 to more than 20 dB. In this thinner specimen, the attenuation of the material is less in play, and the ID notches show high amplitude responses. And these are the data from the small planar reflectors in the fusion phase. The three flat-bottomed holes are also detected with a signal-to-noise ratio of more than 12 dB. The next slide shows the merged data from the Tandem technique. Again, all OD and ID notches are very well detected with a high signal-to-noise ratio. We can see that one of the OD notches, and not even the smallest one, provides a weaker response for both pulse echo and Tandem technique. Most probably, the manual machining process resulted in a very rough sidewall for this notch. The Tandem technique does not provide accurate depth sizing information, but still allows for discriminating ID and OD connected flaws, even in this thin specimen. And here we have the data on the flat bottom holes. The two holes in the lower half of the thickness are very well detected, but the embedded reflector in the near surface region is only marginally visible. This confirms that there is no complete coverage in this zone. The summary of the results for the two-phase array techniques looks like this. The pulse echo technique has a complete green sheet. All reflectors are detected with a signal-to-noise ratio of more than 12 dB. Therefore, it can be used as the only phase array technique for this thin HDPE specimen, offering a complete solution for joints with single-sided access. Although the Tandem technique has slightly better SNR values on most reflectors, the one reflector in the near surface drops to 8 dB. This slide shows data recorded with the TOFD technique on 2 mm deep notches in HDPE base material. We can see that the ID notch on the right is better resolved than the OD notch on the left. This is related to the typical OD and ID resolution of the TOFD technique. And this is TOFD data recorded on the deeper notches in the butt fusion joint. All the reflectors are clearly detected, but accurate sizing is challenging. Indeed, the low-frequency probes do not provide a very good resolution on this thin specimen. We have confirmed that 3.5 or 5 MHz probes could be used to provide better depth resolution. The summary for the TOFD technique looks like this. On this thin specimen, the area with the flat bottom holes could not be scanned with TOFD because there was not enough space on one side of the weld. Based on the information presented in this webinar, we can put forward the following conclusions. Ultrasonic examination of HDPE butt fusion joints presents some specific challenges related to both the material and the possible damage mechanisms in the joint. But we observed that reliable flaw detection and accurate sizing can be achieved on components in a wide thickness range when using combinations of pulse echo phase array, tandem phase array, and TOFD. And we have demonstrated that joints with single-site access can be reliably inspected with phase array only. All three inspection techniques can be implemented with carefully chosen low-frequency probes and optimized high-angle Rexelite wedges for easy field deployment. Zetec's TOPAZ family of high-performance portable phase array units allows to run all the inspection techniques simultaneously in a rapid one-line scanning sequence. And we saw that the UltraVision Classic software is specifically instrumental for setting up Tandem focal law configurations. UltraVision also remains the industry reference for efficient analysis of weld inspection data. This concludes our webinar. I will now turn it back over to Michael for a summary.
On behalf of everyone at Zetec, thank you again for attending this webinar. If you are interested in learning more about our solution or have additional questions, please email us at webinars@zetec.com. To learn more about Zetec, visit our website or follow us on social media. This concludes our webinar. Thank you and have a great day.